Okay, we will talk about drug elimination and clearance in this class um, with more emphasis on renal clearance or renal excretion and hepatic clearance or hepatic metabolism. And in this class, we will talk about elimination in general, not specifically to certain model or certain compartment numbers. And this is an extension of whatever you already know about the clearance and elimination. And you'll find that the majority of this chapter is just a kind of revision of whatever that you know with some extension to other concepts. Okay. For the elimination, we know that the elimination is or consists of two main processes, metabolism and excretion. And we know that the metabolism is the reversible loss of the drug or change of the drug to another entity. So we are losing the drug by changing it or during different metabolism processes into different material. For the excretion is the irreversible loss of the drug is unchanged. And we know that the I can't use. And we know that um, the metabolism is mainly happening in the hepatic or the liver, the majority of it, and the majority of excretion is happening in the renal system or kidneys. Okay, so we will talk a little bit about renal excretion before we go into hepatic metabolism. For the renal excretion, we know that the kidney is the major organ for the excretion. So again, the majority of excretion is happening in the renal system, but as I mentioned before, it doesn't mean that the excretion is only happening in the kidneys. Okay, the functional unit that we have in the kidney is the nephrons, in which we have 1 to 2 million nephron per kidney. We know that the anatomy of the kidney includes many major tubules or structures that includes Bowman's capsule, proximal tubule, loop of Henle, and distal tubule, where the collecting duct. The exact processes of each one of them, I don't care about it. It's you already have it in physiology and anatomy, but in our case, you need to know that those structures are all involved in the excretion, which are parts of the nephrons. What is happening in the nephron that we have a major percentage of the cardiac output that reached 25% of the cardiac output entering the glomerulus, in which the blood that is entering the glomerulus will go out at the end, but in between in the glomerulus we will have some exchange of certain materials from the glomerulus to Bowman's capsule. Okay, and here we have what we call globular filtration process, and it's called by that because it happens in the glomerulus. After which the ultrafiltrate, which is the first thing that is formed in the glomerulus, start to go through different tubules in the nephrons. And again, it's include the proximal tubule, lobe of Henle, distal tubes, and collecting duct. And by the way, this diagram is a simplification of what is happening, but the ultrafiltrate or the filtrate that is produced by by glomerular filtration and the glomerulus will go through different tubules in which we will have tubular secretion, in which more of the material will be secreted to the system or to the nephron parts, and we will have a tubular reabsorption in which a part of the material will be reabsorbed to the body. So accordingly, we will have one or more of those major processes in the nephron or during the renal excretion, glomerular filtration, tubular reabsorption, and tubular secretion. I already know that those processes in different way, and you took it in different courses, but we will talk about them in what we already concerned about in kinetic wise. Okay, so let's start with the glomerular filtration. As we mentioned, is whatever is happening in the glomerulus. It's a passive process, and when we say that it's passive, it means that there is no need of energy. Okay, and one important thing when we talk about passive processes, that and this is important when we talk about passive process or processes in general, we mean that as the concentration, we know that before talking about concentration in the passive process, that the drug moves from the high concentration to low concentration, right? So it's concentration, it goes under concentration gradient, right? So the driving force is the concentration gradient of the drug. And we mentioned that it's passive, so by default it doesn't need energy. Okay, so no need of energy, and we don't have any involvement of transporters or carriers, which is usually needed when we have energy involved. Okay, so in passive processes, as the concentration of the drug increase, the rate of the process increase. As the rate of the drug decreased, the rate of the process decreased. And this is what we know already about what? About linear kinetic or first order kinetic. So this is what I usually kept telling you, just to keep in mind when we talk about first order kinetic. It's not always true, because if it's not first order, if it's not first or linear kinetic or first order kinetic, if it's not passive process, then it's an exception of the linear kinetic. Again, it means that when we are talking about first order kinetics, which is by default called linear kinetic, it's again a passive process by default, because when we are talking about whatever the rate of the process that we are studying or concerned about versus concentration or amount of the drug, it will be a linear or proportionally directly related to each other. Okay, so this thing is very important to keep in mind. Okay, let's go back to the glomerular filtration. Usually, when we are talking about um, passive processes, we are talking about drugs moving again through the membrane without any transporters or carriers. So that's why the molecular weight is very important. As the molecular weight is increasing, the filtration will be decreased as it's size dependent. And I know that you took a lot of information related to the passive transport and fixed first law, in which as the molecular weight increase, the passive processes will decrease, and we usually have cutoffs for the molecular weight that can pass through membranes. Okay, the bound drug or protein bounded drug, either it's bound to blood cells or certain protein, it will not go through filtration. And this is what we usually mention, as I mentioned before, as fraction of the bound drug will not go through a glomerular filtration. If we are talking about unbound or free drug, then it will go through glomerular filtration. And this is for sure common sense, because as the drug binding is increasing with the cell, with the blood cells or with the protein, it means that the size will be increasing. And if the size will be increasing, we will not have glomerular filtration. Okay. And this is what I just wrote here, the free drug or the inbound to protein. It means the glomerular filtration will happen. And as the fraction, let me just write it here. If the fraction of the bound drug increases, then the glomerular filtration will be decreasing. If the unbound or free drug increases, then the glomerular filtration will be increasing. Okay. The first thing that will goes out of the glomerulus or to Bowman's capsule, as I mentioned, it's called ultrafiltrate, and it includes everything. And when I say everything, it's a lot of materials that is toxins that should go out of the body, or other nutrients that still is needed by the body. So the ultrafiltrate that is usually produced at the first step of the excretion, we will just keep it in mind until we go through this concept. The rate of the glomerular filtration rate in the adult male, average adult male, let's say 70 kg and male, is 125 milliliter per minute. Okay, if we change the minute today, so just change this unit to liter per day, you will find that 125 milliliter per minute as glomerular filtration rate is 180 liter per day. And if we think about it, no one can excrete 180 liter per day. Healthy subject, did you ever hear about someone that excrete 180 liter per day? No, for sure. The average urine volume is usually 1 to 1.5 or 1 to 2 liters. Okay. Again, this is the milliliter per minute, which is 180 liter per day. But we end up with 1 to 2 liter per day. And by the way, 1 to 2 liter per day is similar to whatever is the average fluid intake or water intake, which is 1 to 2 liter per day. If you take this and see what is the percentage of 1 to 2 to 180 liter per day, you will find it's just only 1%. So 99% of whatever is filtered is not going out, and that what happens after the glomerular filtration, in which we have what we call it tubular reabsorption. Okay, so this is only 1% of whatever is going through the filtration, and then 99% or the left of that will go through tubular reabsorption, which includes all the material that is needed by the body. Okay, this is a simplification of whatever is happening. The filtrate or the ultrafiltrate that goes through glomerular filtration, or the product of the glomerular filtration, then we go through different tubules to produce the urine. Usually the volume here is large. The volume of the fluid or the ultrafiltrate is large, but the concentration of the material accordingly will be low. But after the reabsorption, which we mentioned, that would be 99% of the volume that is filtered will go through reabsorption. That includes an essential nutrient, water, at different tubules will go through reabsorption, tubular reabsorption. So the volume, total volume will be decreased, and the concentration of the material inside the fluid, which is now called the urine, will be increasing. Okay. Usually we measure the glomerular filtration by material that is only eliminated through filtration, which means that if we are talking about glomerular filtration, we talk about tubular reabsorption and a tubular secretion to produce at the end urine, right? We need a material that goes under glomerular filtration only as elimination, and no reabsorption and no secretion. One of those materials which is used to determine the kidney function is the aniline, and the aniline is one type of polysaccharides that is usually used to determine the kidney function, if it's healthy or not. Okay, the clearance of the aniline should be equal the glomerular filtration rate, which is usually for the average adult is 125 milliliter per minute. The question is, we know now that the aniline is one material that measures the kidney function by determining the healthy kidney function by knowing the glomerular filtration rate. Did you ever hear about, like, if you have any question in clinical practice about the kidney function, that, okay, we have the aniline range in the body that is equal to this and this? Did you ever have it in any of the lab report? We don't. Why? Because we usually use the creatinine, okay? And the creatinine is what is usually used in the clinical practice for now. We have other material that is used in clinical studies that are radiolabeled, which are more accurate than creatinine, but in the clinical practice, we still use creatinine, and we don't see this. Even it's still used in the clinical studies or research-wise, we still have it because it's only going through filtration. For the creatinine, the majority of it goes through filtration, and a slight percentage of it goes through other processes in the renal excretion. But I will keep you with the question why we have this more common in the clinical practice compared to this. I will keep this question with you until we have the discussion per class, inshallah. For the tubular secretion, one of the differences in the tubular secretion when we compare to the glomerular filtration, first, it's not passive, which means it's an active process by default when we are talking about active process. So we need energy, okay? If we need energy, usually we have transporters or carriers, right, to be involved. And if we are talking about active processes, as it needs energy, so it's not linear a process, which mean it's not first order, or what we call it sometimes as non-linear process. So this is one of the exceptions of the linear processes that we have, which means that the rate of the tubular secretion versus concentration of the drug will not give you this profile, and we will see. So it's not linear, so it won't give a linear relationship, and this is important to keep in mind. Okay, it's very important to keep in mind that the concentration versus the rate of the tubular secretion won't be linear. We usually know, or you usually take when you are a little bit in the, I think, freshman and the biology classes, that as the it goes, if we are talking about active processes, it goes against concentration gradient. It's not accurate as a sentence, but we know that as it's transporter and carrier involved with energy, which means it's not as a concentration gradient. So we don't say it goes across the membrane down concentration gradient. It's not. So it depends on the need of the process, or the two sides of the membrane. So we may have it down or against concentration gradient, but usually, okay, against concentration gradient. But it's, again, as I mentioned, it's not an accurate sentence. So we usually say it's the driving force is not the concentration gradient. Okay, so it depends on the need of each part of the membrane, each side of the membrane. Okay, and as we mentioned, it includes transporters or carriers, which means that we have competition. So the tubular secretion is considered one of the main sites of the competition between drugs or between materials that is already taken. And that's why it's one of the major sites of drug-drug interaction, or a drug-herbal interaction in the body or in the renal excretion. Okay, so again, it's an active process against concentration gradient. As we mentioned, it's not accurate. It's usually against concentration gradient, but the driving force, it's not concentration gradient. It's energy dependent. We can say, or we can say here, it's concentration gradient independent. This is more accurate as a sentence. Okay, it's carrier mediated. That's why we have competition and saturation. What we mean by saturation, which you already know that, but we will talk about it anakinetic wise. When we are talking about tubular secretion, it's saturable at a process, as a process, or as we mentioned, is a competition uh, site. Okay, drug-drug interaction site. Okay, saturable, another name for that, capacity limited. Okay, a process, or as we said, non-linear process. What we mean by this, that if you have tubular secretion rate versus concentration of the drug, the rate will increase until we reach a point that it's a plateau because of the saturation. Why we have saturation? Just think about it. Why the saturation happens usually? If we are talking about saturable process that depends on carrier or transporter. Okay, if you have a process that is carrier or transporter dependent, why we have saturation that happens? This is the profile that we have for the tubular secretion. That's why we call it nonlinear, again, because it's not showing a linear profile. Okay, what about protein binding? For tubular secretion and the effect of the protein binding, it was found after the experiment that the effect is not significant of the protein binding. Why is that? Because if we have certain protein, okay, that will bind to the drug, we have the reversible reaction or equilibrium to produce drug protein binding or the drug protein complex, okay? And if we are talking about tubular secretion, we need usually the free drug. Usually the free drug what will bind to, let's say, the transporter, okay? So if we are talking about the drug, we need the drug to bind to the transporter to go through the membrane and to be transported through active processes, right? But we know that the process of the tubular secretion, as we mentioned, as it's active process, it's even it's transporter dependent or carrier dependent, it's concentration gradient independent, right? Which means that I don't need the concentration of the drug to be high at this site to be transported, which means that if the drug, the free drug, uh, um, bind to the transporter or the carrier and passes, and then the free drug at this side is decreased, we will have shifting in the equilibrium uh, of this reaction or of this process to have more of the free drug, so more of the transport. So again, it's dependent on the need of the transport at both sides of the membrane, and it's independent on concentration gradient. So once the free concentration or fraction of the drug is decreased, we will have shifting to this side, according to one of the main principles that we know in chemistry. And I will keep this again for you to remember it. What will cause shifting in the equilibrium to this side if the concentration of the free drug is decreased? So at the end, or the take-home message, that the effect of the protein binding was found to be not significant on the tubular secretion. It's not that effective or will not cause any effect when we compare it to the tubular, the binding of the protein effect on the tubular filtration. Okay. It depends on renal plasma flow, yes, and it was found that as the flow of the plasma increases, the rate of the tubular secretion is decreases because the time needed for the drug to bind to certain transporter or carrier is decreasing, so the tubular secretion is decreased. Okay. As we used aniline and creatinine for the glomerular filtration rate measurement, we need to measure tubular secretion to material that is completely filtered through glomerular filtration and secreted through the tubular secretion, which means that we need material. Again, if we just draw this as just a simplification of the membrane, we have glomerular filtration, we have tubular secretion, okay, of the drug, completely filtered and completely secreted. And this is happens to a material that we know that is called para-aminohippuric acid, okay? And as it's totally or completely filtered and completely secreted with we don't have any reabsorption, tubular reabsorption. So we don't have this. So nothing will go back to the nephron. It means that the clearance of the para-aminohippuric acid should be equal to the complete renal plasma flow. Everything that goes out in the filtration and also in the secretion, which will be around 650 milliliter per minute. Okay, so the last thing that you need to know is the tubular reabsorption. And if we are talking about a process for the tubular reabsorption, it's majorly passive, but sometimes could be active. So it could be saturable, it could be nonlinear, but the majority of the process in tubular reabsorption is passive or linear or first order. Okay, but could have some of the processes as nonlinear. So can the tubular reabsorption be saturable? Yes, it can. Okay. If the drug is completely reabsorbed, if it's filtered but completely reabsorbed. Examples on those materials, we have the glucose and the ethanol. The clearance of them equals zero because if we are talking about complete glomerular filtration, but again, everything that goes out goes back by tubular reabsorption, which means that nothing will go out in the urine. And that's what happens to the glucose and ethanol. And we usually know that if the renal function or the renal system is healthy, we don't have glucose in the urine, right? But if we have some glucose in the urine, this is would be a sign of some disorder or a pathological condition in the renal system, because the healthy case that the glucose would be completely reabsorbed back to the system. Okay. And again, if the drug is partially reabsorbed, which means that the clearance of that drug would be less than glomerular filtration if we consider that is completely filtered, but part of it is reabsorbed, for sure would be the clearance less than the complete glomerular filtration rate. Do we have other clearances or other, sorry, examples of the when the clearance would be equal to zero in general, which means, again, if we have this as a membrane, we have glomerular filtration, we have tubular secretion, we have tubular reabsorption, and we have the urine here formed, okay, after we go through all of these processes, okay. We said that one example of um, the a clearance or the cases in which the clearance would be equal to zero if the drug is completely filtered, but again, it's completely reabsorbed. Do we have other examples of that? Other cases when the clearance of certain material would be equal to zero? Think about it and just think about all of those processes and what would be in which the case that the clearance, and by the way, we are talking only about the renal clearance of the material that goes into a zero. We have a couple of examples on that, and just think about it and see what would be the cases in which the clearance of the drug, the renal clearance of the drug equals zero. Okay, let's go back to the tubular reabsorption. The tubular reabsorption depends on the on two main things. We have the depends on factors that is related to the urine itself and factors that is related to the drug itself, right? The urine effect would be related to the flow of the urine or the pH of the urine. And we mentioned that the pH of the urine is variable. So this variability would affect the ionization of the drug. And if the ionization of the drug is different, then the transport of the drug through membrane will be different. The drug mainly it depends on the pKa of the drug, which again affects the ionization of the drug, so affect the transport through membranes. Okay, and the ionization case or the ionization state of the drug would affect the transport through membrane, whatever if it's linear or non-linear. But we will discuss the effect of deionization of the drug on linear processes or passive processes. Okay, before doing so, we will just go into the effect of the general urine flow or ionization. We know that this is a general rule. If the ionized fraction or unionized fraction of the drug means it's more, it means that the lipid solubility or passing through the membrane would be more, which means more tubular reabsorption would be less excretion. So just take into consideration or be careful when we are talking about the processes. So just again, I will emphasize on this. If we are, just let me draw it again. If we have more glomerular filtration, it means we will have more urine formation, right? If we have more tubular secretion, it means that we will have more urine formation, right? If we have more tubular reabsorption, okay, which means that less urine formation will happen, okay? If we are talking about less urine formation, it means less excretion would happen. And again, I'm talking about each and every process alone. So again, for both of those two processes, if increased, it means more urine formation, which means more more drug in the urine. Let's be more specific. More drug excretion in the urine and drug in the urine. Okay, let me remove this. So if we are talking about more drug in the urine, it means more excretion of the drug. If we are talking about less drug in the urine, which means less excretion of the drug. So just be careful of whatever I'm asking, if I'm asking about excretion or the exact process. If we are talking about tubular reabsorption, let's say, or the excretion of the drug. Why I'm saying so? Because in here, if the fraction of the ionized drug is increasing, it means that more or less of the tubular reabsorption is happening. If less tubular reabsorption, it means the excretion is happening. Okay, more excretion is happening. Again, if it's the opposite, if increase the fraction of unionized drug and the filtrate, it means that more tubular reabsorption, which means that less excretion happening of the drug. Okay, because we are talking about membrane passing or drug passing through membranes. Okay. If we are talking about the urine flow, again, we have normal flow of the urine, which is 1 to 2 milliliter per minute. But again, even if we are talking about unionized drug, which should be preferably passing through membranes if we are talking about passive processes, but still, if we are having more fluid intake, which we mentioned before as factors that affect the excretion or elimination through the renal system. If we have more fluid intake or we are taking drugs such as diuretics, okay, this would affect the flow, increases the flow. If increases the flow, less time for the drug to be reabsorbed. So this would increase the excretion. Okay, if we are talking about the pH of the urine again, which is variable, the this would depends on the intake as food or fluid, on the pathophysiology case or status of the individual, because some of the food intake would affect the pH, either increase it or decrease it, and some of the drug would affect the pH of the urine, so it would decrease it or increase it. All of those would affect the ionization status of the drug, so would affect the transport through membrane, so would affect the reabsorption. This is explained, let's say, as principle-wise or math-wise through what we call it Henderson-Hasselbalch or Henderson-Hasselbalch equation, which is the pH partition theory, in which I will explain it. It's already here, but I will explain it step by step to make it easier for you to understand it or to follow me. If we are talking about, I will talk about weak acids, and everything for weak bases would be the opposite. Okay, so for Henderson-Hasselbalch equation, we have pH equals pKa plus logarithm acceptor over, we have acceptor, right, over donor. For the acids, right, it would be A minus over AH, the ionized, over non-ionized fraction. Okay, so let's say the effect of the, we will talk about the effect of pH first. Okay, so if the pH is increasing, then the ionized fraction would be increasing and non-ionized fraction will be decreasing. If the fraction unionized, if the pH is increased, this would be increased, the same as fraction, sorry, ionized will be increased, non-ionized will be decreased. Then it means the fraction, if it's non-ionized decreased, we have less tubular reabsorption, which means more of excretion. Okay, if the pH is decreased, then the opposite would happen because the ionized will be less, and if the ionized will be less, let me write this fraction. If the pH decreased, less the fraction non-ionized will be increased, so tubular reabsorption increased and decrease of the excretion. And the same thing if I asked about it, or vice versa, which means if I ask about it in a different way. Let's say that we have, if I say that the fraction of the drug that is non-ionized is more, which means this would have, or this preferably would happen at a lower pH. Okay, so I can either start the question or the case from here, or just from here and go back to it. So just be careful of whatever I'm asking, and if we are asking about tubular reabsorption or the excretion, so be careful. Okay, This is the effect of the pH. And again, for weak acids, for weak bases, it would be the opposite because we have the non-ionized over ionized fraction. Okay? If we are talking about the effect of the the effect of pKa, okay? Again, it's the same concept. I will talk about weak acids of one of the cases, and it's the same for the other case. pH equals pKa, right? If we are talking about the effect of the drug, okay? This is the effect of the drug, right? And here the effect of the pH, which means the effect of the urine itself. Here the effect of the drug. We are considering here that the pH of the urine is constant or is not changing, okay? In the first case, we were considering the pKa of the drug is the same, so we are talking about the same drug. And by the way, we can have both of them changing, okay? But just to make it easier for you to understand, this would be log A minus over HA, okay? If the pKa of the drug is increasing, it means the total subtraction of the pH minus pKa would be less, right? The total of this would be less, which means that less unionized fraction that we have, less ionized fraction we have, and more unionized fraction, which means if the pKa of the drug is increasing, or more, which means that if you are comparing two drugs, one of them is higher pKa than the other, it means that the fraction of ionized is increasing because the fraction of the non-ionized. Sorry, the fraction of the ionized is decreasing, the non-ionized is increasing, which means more tubular reabsorption and less excretion. And again, the opposite if the pKa of the drug is decreased. Why is this happening again? If we are talking about large number here for the pKa only, so whatever you are subtracting will be as a total would be less as the number is increasing of the pKa, which means that the ionized fraction is decreasing or the unionized or non-ionized fraction is increasing, so tubular absorption would be more and the expected excretion would be less. Okay, so again, you will have here as equations to summarize whatever you need to determine as fraction of ionized for weak acids or weak bases. But again, I'm not with memorizing those equations. Once you know which one of them is the equation that you need to use, then you are fine to determine the concentration of the ionized drug and the fraction of the ionized drug over the non-ionized drug. I will stop it here in this part of